That was supposed to be my paper. It's supposed to be Lucy's.
I'd say 75 cents to see that.
Okay, before we write anything down, I'll be referencing this term. It's called an ideal gas. Okay? And an ideal gas does not exist. An ideal gas will have all the characteristics they're supposed to have, but we're dealing with real gases, and real gases don't have everything perfect like an ideal gas. Okay? So, I talked to students about, we're going to talk about this kinetic molecular theory because it involves gases. And it involves ideal gases. So every gas that we talk about is a real gas, and an ideal gas doesn't exist. But there are some gases, the way they're put together, they'll have most of these characteristics down really, really well. So the first statement, and then I'll do some drawings because drawings tend to help with each one of these to kind of explain the concept and the idea. So the first one says that when we have gases, okay, they consist of tiny particles, and their size, the size of the particle, compared to the distance that's between them, is negligible. Meaning, the size doesn't take up that much space, and so we're probably going to say that these atoms and molecule size are insignificant compared to the big distances between them. Okay? That's what that statement is saying. So I need you guys to write that statement down. Okay? This is notes. Some of you guys don't like to write notes. Tough. You're going to write this down. Okay? So this is statement number 1. Write it down. And we'll go on to statement number 2 after I give you an example.
Yeah. This is like the only class that the notes make sense. Nope. Every other class feels like you're just like writing.
Well,
there you go.
God, I always give you pins.
There you go.
Here.
How is that going to help you well?
Hey, write it down. Don't talk. You don't have to talk to write it down. And then we can talk a little bit. We can go ahead and do a drawing. So leave a little space after each one of these, and we'll do a little drawing.
I'd like to draw.
Because drawing models, so you guys are going to do a lab. And when you do a lab, you're going to have something happen. And you're going to have to do a drawing of what you think the molecules look like before and afterwards. And the space associated with those molecules before and afterwards. So that you can explain to somebody, that makes sense. This is why this happens. This is why I'm explaining it in this way, and I'm going to use this drawing to kind of help in that process. Models are really, really good if they're used properly. So gases consist of tiny particles. There's big spaces in between them. All right? So I'm going to do a drawing here in a second because I'm going to get rid of this, this slide. Okay? And I can come back to it if you need to finish up something, but I'm going to go ahead and do a drawing.
See what I did here?
What did you do, Trey?
Never. I did. Never shit.
So I want you to draw 2 boxes.
How big would you say? Because that's a different scale than what we got.
Yep. Just draw two boxes similar size.
I'm going to draw my super small.
Can we use the rest of our space?
No.
Cold. Some diamonds.
Wow, those are identical.
Okay. So we have 2 diatomic molecules here. They take up about the same space. They're supposed to resemble boxes that make up the same space. All right? Which one of these 2 would represent that statement better? The one on the left or the one on the right?
The right, I know why.
Why?
Because it's smaller and they don't take up as much area.
Right. Right. So the smaller they are, okay, they don't take up as much space, so this would be more ideal.
I do. Which
Okay? And this is non-ideal. The bigger they are, the less insignificant they are. Meaning, they take up more and more space, and because they take up more and more space, they would be considered non-ideal. This is an ideal. The smaller the molecule, the smaller size of the particle, the more space that you can see in between the particles, and the more ideal it is. Does that make sense?
Is it called rotation?
Now, what if we take this space here and we make it smaller? And we have the same number of molecules in here. We make the volume smaller. What happens to its ideal nature?
Not ideal anymore.
Right. Right, because now you've created less space between the molecules because you made the volume of the container smaller. And if you keep on making it smaller,
It just gets
Eventually it's going to be...
it's gonna dissolve.
Just
Incinerate.
is it going to be... Now these are all assuming they're gases. At some point it's not going to be a gas anymore.
solid.
Right? He could change to a liquid or even change to a gas. Does that make sense? Because the particles are going to be right next to each other. And it's kind of like those drawings we had earlier in the year. We had to decide if something was a solid, liquid, or gas. Remember?
Yeah.
And if they were close to one another, we said that was a liquid. If they were touching each other, we said that was a solid. And these are gases.
Yeah.
Okay? So the opposite can happen too. If this comes down here, and then we create
Big old bonds.
much bigger space for these to operate.
Wow!
Now it's more ideal. Does that make sense? Okay. So the closer they are, the less ideal they are because the distances, the size of the particle is not insignificant anymore. Make sense? Okay. We move on. On the left. Okay. This one I'm not going to draw a picture for. I'm going to look at the next one. So gas particles are always in constant motion.
Kind of like me. I'm a gas mark.
Yeah, you'd be more of an ideal gas, right? Because you're always in motion. Okay? So gas particles are always in constant motion. There's a second part to this. The collision between those particles and this, there are going to be collisions between other particles in the side of the container holding them. So these particles, if they're in a container, they're always moving. And then there'll be collisions that'll take place because they can't move in a straight line forever. What they'll do is they'll move in a straight line, they'll hit the side of the container, they'll bounce off, and they'll continue to move without losing any energy. So like in this room, we got gas particles, and they're moving. They're hitting one another. They're hitting the side of the container. They're hitting their inner ear, creating pressure on the inner ear. Because you guys know as you go to different altitudes, you go higher and lower pressure, then you have less and more collisions on your ear, and that's why your ear gets, like you go down in water, there's more pressure on your ear because there's more collisions on your ear. And that's what creates the pressure on your ear. When you go to higher altitudes, there's less collisions on your ear. And that's why you have to chew gum or yawn or kind of try to equalize that out yourself. But they're always in constant motion, and the collisions are going to take place between themselves and one another and the sides of the container.
So when you pop, like when you pop them, why is it all sudden stop?
Because what happens on the inside of your ear will equal to the outside of the air when it pops. So that the pressure inside and outside is the same, so there won't be any
So
pressure.
you like basically open a valve?
It doesn't open a valve. when you yawn, there's something in here that allows that equalization of pressure into inner ear versus the outer ear.
An accumulator is what I would.
Okay, questions on that you have? All right, next slide. Did you guys write that down?
Yeah.
Okay.
Did you get it?
Picture time. Oh.
What?
No picture.
No, because it'll be combined with this one. Okay?
Okay.
So, because the last class I did a picture, and it really works with this second one, the combination of these two, when I show it. Okay, so, number 3, when we talk about these collisions that are taking place, they're perfectly elastic. What does that mean? Elastic means there's no loss of energy. So, when cars collide with one another, okay, most of the time they're not very elastic, right? When a car hits something that's immovable, like a pole or something, okay, it sticks there and it doesn't really bounce off much. Now, it could bounce off, but there's a likelihood it's going to slow down and it's just not going to bounce back off, okay? So, these collisions are like a basketball that you drop and it just continues to bounce forever and doesn't slow up. The reason why these can collide and not lose energy is because they're really, really small. And they have a characteristic of an elastic collision. An inelastic collision is one where something hits, it sticks. And it doesn't bounce off. So when these hit the side of the container and one another, they don't stick together. They bounce off one another and they continue to have their same amount of energy before and afterwards. So that energy doesn't change in them. Okay? So we say that their collisions are elastic. That the energy before and the energy afterwards is the same. So down here, at the bottom of the page, it says kinetic energy is energy in motion. And there's two things it depends upon, the mass and the speed of the particle. So if you look at this equation, kinetic energy equals 1/2 mv squared. Kinetic energy goes up if the mass goes up, and kinetic energy goes up when the speed goes up. And the speed is what we're going to look for when we take a look at some of these examples. Okay? We're going to look at the speed more than anything.
I have to say equation.
Yep, that's for kinetic energy. Now, we're not going to use that equation to solve any problems, but we will use that equation to kind of understand how velocity affects kinetic energy of the particle. And in a way, kind of the mass does as well. So 1, we say that there's big distances between particles, and the particle size, smaller it is, the better for being an ideal situation. The second thing that we say on the previous slide, their particles are always in constant motion. So that they're always moving, and there's collisions that take place. And those collisions are going to be elastic, which means they don't lose energy. So these are gases. These are ideal gases that take on these characteristics. And we say all these gases are going to have elastic collisions when they take place. Okay. And then I'm going to do a drawing after the next slide number 4 to get all these, because these all work together.
Do they both like bounce away like magnets, like they just don't want to hit, or do they hit?
No, they'll hit and then they'll bounce off, kind of like
There's
pool
one-
balls on a pool table.
Okay,
Same type of
So
collision.
none of them like hit and then one stays and then one goes, or like do they hit and they both go?
Well, they can go different velocities.
They just don't stick in general.
Right, they won't stick together.
Interesting. Now what?
Okay, there's 2 more slides. Number 4. So, previous slide talked about kinetic energy and energy associated with the speed of a molecule and its mass. and both of them have a play in their overall kinetic energy. So this statement says that the kinetic energy, which is 1/2 mv squared, is directly proportional to the temperature, which means as the temperature goes up, what happens to the kinetic energy?
It
Goes up.
increases.
And when the temperature goes down, kinetic energy goes down. So within a mixture of gases, all gases are going to have the same average kinetic energy. Okay, they're all going to have the same temperature in a mixture. In this room, we got oxygen, nitrogen, and some other gases. And they all have the same kinetic energy, okay, associated with them. So after you write that down, I'm going to go ahead and do a drawing, and the drawing is going to have some things different than the first one. And we'll talk about these last three characteristics. Okay, that gases are always in constant motion, the collisions are elastic, and the temperature and kinetic energy have a direct proportion, a direct relationship. Okay, and then the last one's pretty easy too. We probably won't show much on a drawing for
So
that.
the different for like water molecules?
Water molecules as a gas would be the same for all gases. So that all gases will have these characteristics. So vapor water have these characteristics, but not liquid water, because that's a liquid phase. And we're only talking about gases. So all we're talking about is gases. Okay?
Gas is smoke. What kind of gas is it?
Smoke is actually small solid particles that's in the air. Could be ash, could be even smaller than that though. Because smoke particles are solid particles and they spread out. Because eventually they'll settle out.
That's why, like, when you burn wood, it's not actually. That's like the wood that's burned, it's smoke, right?
It's a combination of vapor, combination of solid particles. Yeah, because it's there's going to be some solid particles that are in there that are really light that eventually will settle out. Okay.
I bet that answered the question. It's not a gas. It's actual solids that are floating. Do it. That'd be terrifying.
I'm getting old.
I'd get Omega.
Okay, so you're going to put this under number 4. Alright? And then we're going to add some things to this. Shh. We're going to add some things to this. So that this variable doesn't, like the last one, these are all going to be the same size.
Are the boxes meant to be different sizes? Or
They're supposed to be the same size.
okay. I just didn't know.
Alright, we're going to add something to this side, and you guys tell me some information, what you think this would represent.
Not your bad.
Okay, go ahead and do those drawings. There's something real similar to what we have up there. So if we were drawing a key, we don't have to draw a key for the molecule because we know it's diatomic. We know it's a gas because there's spaces in between it, so we don't have to describe that. They would be closer, they would be on the bottom of the container if they were liquid or solid. So we know they're gases, they want to take up the the container, fill the container up, which showing it this way kind of shows that. What do you think the arrow represents?
Interelastic or whatever.
Well, it can here. So this arrow going in this direction eventually will bounce off this side of the container and bounce off. And the arrows, what can you tell me about the arrows? The direction, right? That they're moving. But what else can you tell me about the arrows? What do they all have in common?
Same size.
Same length. Okay? So that tells you, the same length tells you the magnitude of their speed and how fast they're going. So these are all going about the same speed. Do you agree? How does this one's speed compare to the speeds over here?
Those are faster.
These are faster. So in physics, if you take physics or do anything with physics, the arrows represent magnitude of it gives you two things.
Velocity.
It gives you velocity, gives you a direction, and it gives you a speed. Okay? So it gives you two things. So if you notice, as this hits, it comes off with the same magnitude. This one comes off at the same magnitude after it hits. So they're not losing any energy. So one thing that this drawing shows is that speed is not affected by the collisions. The collisions are perfectly elastic. They don't lose any speed. This one comes down here. If it hits off, it's going to be going the same speed when it bounces off. Same with these. These go the same speed. So this arrow means, gives you indication about the velocity of how fast the particle is moving. Can you guys indicate what kind of collision this one is going to be versus a collision that takes place here? Which one has a more forceful collision? The one on your right, the one on your left?
Right, because it ricocheted.
Well, they both ricochet.
That
But,
one goes in a different direction.
These are
that
the
one goes right back to itself.
right, but these are about the same size, but this one is faster than this one. So this collision, this force, is going to be bigger here, and this force is going to be smaller. That force is bigger than this force
Because of velocity.
because of velocity.
And it would also matter if it had a weight, like inertia.
Right. So if this was a bigger molecule and going the same speed, it's going to have a
Much greater.
greater force. So does anybody know what the term is where we take force over area? Does anybody have a term for
What's that start with?
P?
Newtons, no.
No. Force is in newtons.
No, what's the next letter?
R.
What's the next one?
No, I know this.
E. P-R-E-S.
Pressure.
Pressure.
Oh, come on.
Okay? Listen.
I didn't know I was getting that with the letter P. I was saying like, well.
Okay. If you apply a force, over an area, the bigger the force, the bigger the pressure. So, which these two gases have a greater pressure in the container? The right or the left? The right has a greater pressure because it's more forceful, and the F is bigger, the area is about the same because it's the same size of molecule. So, we are going to talk about which of these two have a greater temperature. One on the right or one on the left.
At contact or just...
No. Just when looking at the gas's temperature, which one has a greater temperature?
Left.
Why the left?
They're faster.
Okay. You think these are faster?
Those are slower.
Those are slower. They
No,
got
no,
less
no.
of an arrow, bro.
They're slower. So, temperature, molecules, are they going to be moving faster if it's a higher temperature or slower? Faster. This is a higher temperature. What if I heat this up? I go ahead and decide to heat this guy up, add temperature to it. What's going to happen to the size of the arrow?
Go faster.
increase in length.
Boom.
Come on.
These other ones I can't show.
Yes.
But they're going to be longer arrows. Is there any rhyme or reason to the direction that they're moving? No. They're in rapid, random motion. Now, if I cool this down, this one I cool down, what happens to the size of the arrows?
Give me a little nub.
Small. What happens to the force of the collisions? They're less, right?
It's kind of like molasses. You heat it up. It's more like, or oil. Oil would be a great example.
Okay.
It's cold and thick, slow.
Yes.
Could there be like a point where they can just stop?
Yes.
That's
Yeah.
called negative 32.
It's called absolute zero. We'll talk about it. It's a place that hasn't ever been reached. It's a theoretical point saying that you can take particles and you can stop their motion.
Freeze them.
You can't do it. Because even if they get to where they're close together, they're going to be moving back and forth. And the thought is, can we get to a point where they don't move at all and it's never been reached?
How close have they got?
Like within a millionth of a degree.
Really?
They got that close.
Yeah.
Oh, that sucks.
But it's still moving. It's still moving. It's called absolute zero. That's when motion ceases to exist. Now, there's one last thing I need you guys to write down.
How do they even use the thing? How do they make it that cold in the first place?
Good question. Probably about, I don't know, it's been a long time ago that these guys up in Boulder, they created a situation, at the University of Colorado, where they would use beams of lasers in all different directions on a sample of matter, and they would cause it to slow down to basically non-existent motion, and they measured the temperature. But the theoretical point is like a minus 273.15, and it goes on. And they were able to get it to like a minus 273.15. But the last digit still wasn't what it theoretically was supposed to be. So it's never been
Laser.
reached.
Usually those create heat.
Here's the deal. Here's the deal with absolute zero. You can't have any volume. So do you think if we get this to where it's not moving whatsoever,
It has to
will its volume? Will it still have volume?
Mhm.
Will the gas particle itself still have volume?
Yes.
Yeah. So that's why it's a theoretical point, because they say, well, it still has, theoretically it shouldn't have any volume anymore, but there's still substance there.
I wonder
So
what
that's why
happens
it
if it stops. Does it
they
disappear?
haven't got to
Does
that
it
point.
disappear?
No, they haven't. Well, they haven't got to that point
That's
yet.
what I mean. It might disappear if it stopped. Where the hell did it go?
Okay. This is the last one, and this is pretty important too. And then we're
boy.
going to give you 5 statements before you go, for each ideal and non-ideal. So, go ahead and write that down for your 5th statement. Shh, listen. We're going to do we'll do a little drawing for this one, and then we're going to give you 5 statements before you go.
Oh boy.
So, molecules, if it's ideal, are not going to have any attractive or repulsive forces between them. That's saying that when 2 molecules come in close proximity to one another, there'll be no attraction whatsoever between those particles. And there'll be no repulsion, meaning they won't repel one another either.
So they're not gonna do anything.
if we have 2 molecules slide past one another in a gas, there will be no forces
Exerted.
of attraction or repulsion between those particles. That's what an ideal gas will have. It has no attractive forces between them. And so that would be another scenario where we wouldn't have any attractive forces.
That's the same gas. I mean, what if you had oxygen and nitrogen? No, wait, what's not a gas?
No,
Helium.
just one type of gas.
So just oxygen molecules.
Oxygen molecules attracting for one another. Okay. Everybody got that down?
Yeah.
All right. All right. I got one more drawing to show underneath this one.
Turn around.
Yeah.
Pay attention.
I thought I heard my name.
You just did.
Wow.
The one on the right's ideal. The one on the right's ideal.
Okay, so when you're looking at these two, looking at that last one, look at the distance between these two. Even if they do go past one another, they're smaller and there's bigger distances between them. This is more ideal because there are bigger spaces between them. Because if they slide past one another and they're really close, then there's going to be attractive forces. If these try to slide past one another, then they're less ideal because they're closer to one another. See, if they get really close to one another, then they're less ideal. If they're farther apart, they're more ideal. So, last statements, just like I asked you guys about 4 things that you would like to see in a guy or a gal that would be ideal. We're going to have scenarios that would be ideal and non-ideal. Okay? So, we usually kind of go back and forth. We fill in both at the same time. So, what's an ideal gas? Tell me some characteristics of an ideal gas. Yes?
Distant.
Gases take up large volume.
Okay, so we want a gas that has large volume. Good.
Greater distance?
That will create greater distances.
Okay.
Okay? So non-ideal would be
Smaller volume.
smaller volume. Okay? Okay, what's another one? What do we look for?
Force.
What's that?
Small particles.
Yes. Small particles. And then non-ideal would be large particles. Very good. Okay, what else?
Constant.
What's that?
Constant.
Okay. Ideal is constant motion. And non-ideal would be
Immobile.
Weird motion.
very little motion. Okay, what else? There's some more dealing with speeds and velocities and those type of things. So,
Direction.
what about the collisions? If they're ideal, they're going to be what? Elastic. If they're non-ideal, they would be what?
Non-elastic.
We call them inelastic.
Inelastic. In Alaska.
Hey, Chase, is that Dairy Queen brand?
What?
Is that Dairy Queen?
One more.
One more?
Yep.
For each or?
Yep. One more for each. What do you know about? What do you think if it's ideal when we take a look at temperatures? Which one would be
Cold.
which is higher?
Hotter.
Which one's higher?
Ideal.
Ideal.
What?
Well, I mean, I'd rather be hot on a cold.
Higher temperatures because they move
Oh.
more motion. So higher temperatures. And this would be lower temperatures.
Is that Burger King?
Okay, finish it up here. An ideal gas has these characteristics. They are large volume, small particles, they're always moving, they have elastic collision, and they usually have higher temperatures. Non-ideal, smaller volumes, large particles, very little motion, inelastic collisions, and lower temperatures. Okay?
You know what? That's awesome. We're getting into physics here.